Hey guys, how do you prepare a topic for competitive exam like GATE? Do you simply understand the concept or do you try to practice questions based on that topic? Sometimes, even after studying a topic, we may not be able to solve all competitive exam questions based on that. Why it is so? Any idea? In fact, when you prepare a topic for competitive exam, it's better to practice maximum possible previous year questions based on that. So, today I have brought something interesting for you. In this video, I'm going to share detailed solution of previous year GATE questions from 1999 to 2020 on the topic maximum power transfer theorem. Are you ready to start? Alright, hope all set to get started. As I told you earlier, today we are going to solve all previous year GATE questions on maximum power transfer theorem. So let me ask you something. Do you know what is maximum power transfer theorem? In fact, all about maximum power transfer theorem is discussed in my previous video. The link of that video is given in description box. If you have any doubts regarding maximum power transfer theorem, please do watch that. Now, let me take you to the first question. It's from GATE 1999. Here, we are asked to find out the value of R in ohm required to maximum power transfer in network shown below. The network is given here. 4 options are also given. Option A2, option B4, option C8 and option D 10. Let us first understand this question. Here we are asked to find out the value of load resistor R such that maximum power transfer takes place from source network to load resistor. Based on maximum power transfer theorem, we can say that power transfer to R will be maximum when R is equal to Thevenin's equivalent resistance of the source network. Now, have a look at the network given in question. Here, R is the load resistor and this is our source network. For maximum power transfer, this load resistor R should be equal to Thevenin equivalent resistance of this source network. So what we are going to do next is we are going to find out Thevenin equivalent resistance of this source network. Do you remember what is Thevenin equivalent resistance of a network and how to calculate its value? In fact, Thevenin equivalent resistance is nothing but the internal resistance of the source network looking through open circuited load terminals. For finding out its value, we are supposed to set all sources present in the network to 0 and calculate internal resistance looking through open circuited load terminals. Now, let me ask you something. How can we set sources present in the network to 0? Any idea? Alright, we can set an independent voltage source to 0 by replacing it with a short circuit and an independent current source to 0 by replacing it with a open circuit. Got it? Now look at our network. Here this is our load terminals. We have to open circuit these terminals for calculating Thevenin equivalent resistance. Then we have a 3 ampere independent current source which should be replaced with a open circuit. Finally, a 25 volt independent voltage source and it should be replaced with a short circuit. After doing these modifications, we get a circuit like this. X, Y are the open circuited load terminals. When we look from open circuited load terminals, this 5 ohm and 20 ohm are connected in parallel. And this parallel combination and this 4 ohm resistor are connected in series. So we can write the Thevenin equivalent resistance RTH is equal to 5 parallel 20 plus 4, that is equal to 4 plus 4 equal to 8 ohm. Thus, we obtain Thevenin equivalent resistance of the source network. Now we have to equate that to load resistor for maximum power transfer. So we write RL is equal to RTH is equal to 8 ohm. Our answer is option C, 8 ohm. Clear? Hope you got it. Moving on to next question. It's from GATE 2002. In the network of the figure, maximum power is delivered to RL if its value is dash. You can see the network here. 4 options are also given. Option A 16 ohm, option B 40 by 3 ohm, option C 60 ohm, and option D 20 ohm. As you know, a network delivers maximum power to load resistor RL when RL is equal to RTH. Now have a look at the network given in question. This is our load resistor. So we have to open circuit this load resistor and calculate Thevenin equivalent resistance. When we open circuit, we get a network like this. VTH is marked as open circuited voltage across the load terminals. Here you can see a node. By inspecting the network, it is clear that the node voltage and VTH are same. So let us label this node voltage as VTH. Now you look at this source. It's a dependent current source where the controlling variable I1 is defined as current through this 40 ohm. Since we are having a dependent source in the network, it's not possible to directly calculate Thevenin equivalent resistance, which means RTH should be calculated by using the formula VTH by ISZ, where VTH is the Thevenin equivalent voltage and ISZ short circuit current across load terminals. Let us first calculate VTH, which is nothing but the open circuited voltage across open circuited load terminals. So for calculating that, we are going to write KCL at this node. At this node, we have one incoming current 0.5 I1 and 2 unknown currents. The unknown currents are the current through this 20 ohm and that through this 40 ohm. When we write KCL at this node, we have to take all unknown currents as outgoing currents at this node. The current through this 20 ohm from node VTH to reference node can be written as VTH minus 0 by 20, that is VTH by 20. Similarly, the current through this 40 ohm in downward direction can be written as VTH minus 50 by 40. By KCL, sum of currents entering at a node is equal to sum of currents leaving that node. So we can write 0.5 I1 is equal to VTH by 20 plus VTH minus 50 by 40. Here left hand side represents sum of currents entering the node and right hand side represents sum of currents leaving the node. Now you look at this network. You can see I1 is defined as current through this 40 ohm in downward direction. One end of this 40 ohm is at potential VTH and other end is at potential 50. Correspondingly, the current through this 40 ohm in downward direction is equal to VTH minus 50 by 40. So we get I1 is equal to VTH minus 50 by 40. By substituting the value of I1 in this expression, we get 0.5 into VTH minus 50 by 40 is equal to VTH minus 50 by 40 plus VTH by 20. Then by rearranging, we get VTH is equal to 10 volts. Clear? Alright. Our next task is to find out ISC, which is nothing but short circuit current across the load terminals. This is a network given in question. Now let us short circuit this load resistor RL and calculate current across it. When we short circuit RL, we get a network like this. Now you look at this 20 ohm resistor. You can see a short circuit parallel path across it. Hence there is no significance for this 20 ohm So we remove this 20 ohm and get a circuit like this. Let us label this as node 1. Now what we are going to do is we are going to write KCL at this node. By inspecting this node, it is clear that there is one incoming current 0.5 I1 and two outgoing currents I1 and ISC. By KCL, sum of currents entering a node is equal to sum of currents leaving that node. Hence, we can write 0.5 I1 is equal to I1 plus ISC. It is written here, 0.5 I1 is equal to I1 plus ISC. I1 is defined as current through 40 ohm in downward direction. One end of this 40 ohm is at reference node, that is at 0 potential, and other end is at 50 volt potential. Correspondingly, the current through this 40 ohm in downward direction can be written as 0 minus 50 by 40. So we get I1 is equal to 0 minus 50 by 40, that is equal to minus 5 by 4. Then by rearranging this equation, we can write ISC is equal to 0.5 I1 minus I1. Finally, by substituting the value of I1, we get the short circuit current ISC is equal to 5 by 8 amperes. Clear? Thus, we obtained the values of VTH and ISC. So what we are supposed to do next? We are supposed to calculate the value of RTH by using the formula VTH by ISC, that is equal to 10 by 5 by 8, that is equal to 16 ohm. For maximum power transfer, the value of load resistor should be equal to Thevenin equivalent resistance of source network. Correspondingly, we can write RL is equal to RTH is equal to 16 ohm. Thus, our answer is option E. That's all about this question. The next question I have for you is from GATE 2005. The maximum power that can be transferred to the load resistor RL from the voltage source in the given figure is dash. The circuit is given here. Now have a look at the four options given. Option A 1 watts, option B 10 watts, C 0.25 watts and option D 0.5 watts. I think you can pause the video and try to solve this question yourselves. It's very simple. Finally, you can check your answers. Alright? Hope you all try to solve this problem yourself. Now, let's have a look at the correct answer. As you know, maximum power will be delivered to RL when RL is equal to Thevenin equivalent resistance of the source network. Here, source network is already given in Thevenin equivalent form. Hence, we can directly find out the value of Thevenin equivalent resistance. What's the value? Any guess? It's nothing but 100 ohm. So we can say that this source network delivers maximum power to this load resistor when RL is equal to 100 ohm. RL is equal to 100 ohm. Here we are also asked to find out the value of maximum power, which can be mathematically expressed as VTH square by 4 RTH. By inspecting the network given in question, it is clear that VTH is 10 and RTH is 100. Then by substituting these values, we get Pmax is equal to 0.25 watts. Clear? Thus our answer is 0.25 watts. Simple, isn't it? Alright. Let me now take you to next question. It's from GATE 2009. In the circuit shown, what value of RL maximizes the power delivered to RL? Circuit is given here. Now have a look at four options given. Option A 2.4 ohm, option B 8 by 3 ohm, option C 4 ohm and option D 6 ohm. Let us first analyze the network. Here we are asked to find out the value of RL so that this source network delivers maximum power to RL. As you know, a source network delivers maximum power to load resistor when load resistor value is equal to Thevenin equivalent resistance of the source network. So what we are supposed to do next is we are supposed to find out Thevenin equivalent resistance of this source network. Clear? Since we are having a dependent voltage source Vx in the source network, it's not possible to directly calculate Thevenin equivalent resistance, which means it should be calculated by using the formula Vth by Isc, where Vth is open circuited voltage across open circuited load terminals and Isc is the short circuit current across load terminals. Let us first focus on Vth. When we open circuit load terminals, we get a network like this. Since these terminals are open, there is no current flow through these two forum resistors. Correspondingly, there is no voltage drop across it. And if we write KVL of this loop, we can directly equate Vth to 100 volt. VOC or Vth is equal to 100 volt. What is our next task? Any idea? Alright, our next task is to find out value of Isc, which is nothing but short circuit current across the load terminals. This is a network given in question. When we short circuit this load resistor, we get a circuit like this. Let us label this as Isc, this current as I1 and this current as I2. Here I1 is defined as current through these two series connected resistors from left to right. You can see this 100 volt source is connected across this series combination of 4 ohm resistors. Hence we can write I1 is equal to 100 by 4 plus 4. That is I1 is equal to 100 by 8, that is equal to 12.5 amperes. Clear? Now you look at this dependent source Vx, where the controlling variable Vx is defined as voltage drop across this 4 ohm with a negative polarity at left end and positive polarity at right end. I1 is the current flowing through this 4 ohm from left to right. You know, voltage drop across a resistor can be mathematically expressed as product of resistance value and current through it. Hence we get Vx is equal to minus 4 into I1, that is minus 4 into 12.5. Why there is a negative sign? Any idea? Look at this. Here Vx is defined as voltage drop across 4 ohm with negative polarity at left and positive polarity at right. And I1 is defined as current through this 4 ohm from left to right. Hence, it develops a voltage drop across 4 ohm with a positive polarity at left and negative polarity at right. That's why there is a negative sign and we get Vx is equal to minus 50 volts. Clear? Now, you look at this current I2. It is defined as current through this 4 ohm from left to right. One end of this 4 ohm is Z potential plus Vx and other end is Z potential minus 100. Correspondingly, current through this 4 ohm from left to right can be expressed as Vx minus 100 by 4. That is equal to Vx minus 100 by 4. By substituting the value of Vx, we get I2 is equal to 12.5 amperes. Clear? Now let us write KCL at this node. At this node we have one outgoing current Isc and two incoming currents I1 and I2. By KCL, sum of incoming currents entering at a node is equal to sum of outgoing currents leaving that node. So we can write I1 plus I2 is equal to Isc. I1 and I2 are already calculated. Correspondingly, we get Isc is equal to 25 amperes. Then by substituting these two values Vth and Isc in the expression of Rth, we get RTH is equal to 4 ohm. For maximum power transfer, RL should be equal to RTH. So we get RL is equal to 4 ohm. Thus our answer is option C. Now let's see a question from GATE 2011. In the circuit shown below, the value of RL such that power transferred to RL is maximum is dash. You can see the network here. Have a look at 4 options given. Option A 5 ohm, option B 10 ohm, option C 15 ohm and option D 20 ohm. Let us first understand the question. This is the network given. Here we are asked to find out the value of this resistor RL such that this source network delivers maximum power to RL. As you know, a network delivers maximum power to load resistor when RL is equal to Thevenin equivalent resistance of the source network. So, first we have to calculate Thevenin equivalent resistance of this source network and then equate that to load resistor RL for obtaining maximum power transfer. And for calculating the Thevenin equivalent resistance, we are supposed to replace all independent voltage source present in the network with the short circuits and all independent current source present in the network with open circuit. By inspecting this network, you can see 2 independent voltage sources 5 volt and 2 volt and 1 independent current source 1 ampere. These 2 independent voltage sources should be replaced with the short circuits and this current source with open circuit. Apart from that, this load resistor RL should be open circuited. After doing these modifications, we get a network like this, and as you know, Thevenin equivalent resistance is the internal resistance of the source network looking through open circuited load terminals. When we look from this side, this 10 ohm and this 10 ohm are connected in parallel and the parallel combination is series connected with this 10 ohm resistor. So we can write RTH is equal to 10 parallel 10 plus 10, that is equal to 15 ohm. For maximum power transfer, RL should be equal to RTH and we get an answer option C. Hope it is clear. Moving on to next question. It's from GATE 2016. In the circuit shown in figure, the maximum power in watts delivered to resistor R is dash. The circuit is given here. As you know, for maximum power transfer, R should be equal to RTH, and since we are having dependent sources present in the network, RTH should be calculated by using the formula VOC by ISC, where VOC or VTH is the open circuited voltage across open circuited load terminals and ISC is the short circuit current across load terminals. Now have a look at the network given in question. This is our load resistor. Here you can see one independent 5 volt voltage source and one dependent voltage source 100 V0, but the controlling variable V0 is defined as voltage drop across this 2 kilo ohm resistor. Let us first calculate VTH or VOC, which is nothing but the open circuited voltage across these load terminals. When we open circuit load terminals, we get a network like this and VOC is marked as voltage across it. It is clear that VOC is the voltage drop across this 40 kilo ohm resistor. This 40 kilo ohm and this 10 kilo ohm are series connected. 100 V0, the dependent voltage source, is connected across this series combination. So we can easily find out the value of voltage drop across 40 kilo ohm using voltage division rule. Hope you are already aware of that. So VOC is equal to 100 V0 into 40k by 40k plus 10k, that is equal to 80 V0. Thus we obtained the value of VOC in terms of V0. So what we are supposed to do next? you're supposed to find out the value of V0. V0 is defined as voltage drop across this 2 kilo ohm resistor. This 2 kilo ohm and 3 kilo ohm are series connected, and this 5 volt source is connected across this series combination. So we can easily find out value of this V0 using voltage division rule. That is, V0 is equal to 5 into 2k by 2k plus 3k. So we get V0 is equal to 2 volts. By substituting the value of V0, VOC becomes 160 volts. Clear? Our next task is to find out ISC, that is short circuit current across load terminals. This is our load terminals. When we short circuit these terminals, we get a network like this, and ISC is marked as current across it. You can see this 40 kilo ohm and the short circuit path are connected in parallel, hence there is no significance for this 40k. So we remove that resistor and get a network like this. Here, the controlling variable of this dependent source V0 is defined as voltage drop across this 2 kilo ohm resistor. This 2 kilo ohm and 3 kilo ohm are connected in series, and 5 volt source is connected across this series combination. So we can write the expression of V0 as 5 into 2k by 2k plus 3k. It is by using voltage division rule. So we get V0 is equal to 2 volts. Clear? Okay. Now let us find out this ISC. It's a current through this 10 kilo ohm resistor. 100 V0 voltage source is connected across this resistor. Correspondingly, we can write ISC is equal to 100 V0 by 10k. ISC is equal to 100 V0 by 10k. By substituting the value of V0 as 2 volt, we get ISC is equal to 20 milliamperes. Thus, we calculated the values of ISC and VTH. Then by substituting the values in the expression of RTH, we get RTH is equal to 8 kilo ohm. Hope you remember, in the question we are asked to find out the value of maximum power transferred, which can be mathematically expressed as VOC squared by 4 RTH. Finally, by substituting the values of VOC and RTH, we get Pmax is equal to 0.8 watts. Okay? That's all about this session. If you have any doubts regarding this, please do let me know in the comment section. I will definitely clear your doubts. Thanks for watching. Thank you.